Welcome, and thank you for joining us in this podcast today with Dr. Anis Rahman, President, Chief Technical Officer, and inventor of T-Ray Technologies for Applied Research in Photonics Incorporated, ARP. My name is John Mahoney, President of C4 Technology. C4 Technology engages in technical sales and innovation discovery solutions for semiconductor and broader industry applications. Today, we are discussing with Dr. Rahman silicon carbide. Silicon carbide, of course, is used extensively in the power applications, automotive power applications, and optoelectronics in the semiconductor industry. Today, Dr. Rahman will be discussing the T-ray teraspectrum metrology of a whole silicon wafer mapping by T-ray imaging. Dr. Rahman, thank you and welcome.
Thank you, John, and thanks for continued arrangement of this podcast series around the T-ray metrology and T-ray imaging, spectroscopy, and all others. So today, as you mentioned, we are here to introduce our T-ray technology for silicon carbide wafer investigation. And see a few things that probably of importance. So again, here is a little bit of background of our efforts at Applied Research in Photonics, as you said, ARP, and homegrown technology over the years of research. Finally, the fruition in the cameraless imaging of lattice scale with bigger wavelength, and particularly with terahertz radiation or T-ray. So going into the silicon carbide issue, as you know, that silicon carbide is important semiconductor for high power, high temperature applications, where silicon itself is not as effective. And the silicon carbide, unlike silicon, requires pretty high temperature processing for its single crystal growth. So that's one of the basic difference, although we can produce, our industry can produce pretty big ingot or bull, as they call it, almost stretching to a meter or less than a meter. But we discussed about gallium nitride before. It's way more advanced than gallium nitride because minimum half a meter bull is routinely grown. Only difficulty is that it requires very high temperature, close to 2200 degree or above, sometimes even 3000 degree treatment for the vapor deposition, physical vapor transport, as they call it. So what we are trying to do here is to see the physical vapor transport, also known as the seeded sublimation deposition, and then how the wafers are coming out of it, and comparing all other techniques like TEM image or SCM, which shows the surface, and frozen in time, if it's one slice at a time. So T-ray as an alternative not only can image the whole wafer, but also it can see layer by layer across the depth without destructive technique, without breaking it. no sample preparation needed. So it can get the volume image, the layer by layer, and imaging can be done both in reflection mode and transmission mode. So this technique offers quite a bit advantages, such as T-ray can see more. That means it can see below the surface, and as I said, layer by layer, and it can see small features. Nano-scale to sub-Angstrom, less than an angstrom resolution can be achieved, can be done, and is being done routinely by our technique. And it sees more clearly, where any feature can be seen the way it is, very, very clear. The most clarity is from this technique obtainable. Silicon crystal, again, silicon carbide crystal is grown at high temperature, as I said. So there are impurities that are present in the process that gets into the boule or ingot. And because that ingot is sliced into wafers, they remain in the wafer as well. And up until now, industry has not been able to see this big picture, because when you make a TEM sample to see what kind of things are there, you're focusing on a very small area of few micron. So anything you see there as a tip, or as, think about it, let's say I had a triangle of some sort, or a hollow triangle, pyramid or something. If you cut that, and if you look at on one edge, you may think of something. But if I see the whole structure, then I can see, oh my God, this is a triangle of some sort or something. So that is the whole point here. Full fatty image with high resolution is able to show us all the things that's happening in the ingot, and which is also in the wafer. So again, here's a little bit of background of T-ray, the way we generate T-ray or terahertz radiation, what we call is a dendrimer dipole excitation technology. And this is due to the dendrimer material that was originally invented by Don Tamalia. And then at our company, we found a way to modify that dendrimer to make high Chi2 material or high electro-optic coefficient material, and then pump that particular material in a particular orientation to generate the terahertz radiation. So this is the basis of the Rahman-Tamalia effect. And as the energy band diagram here shows a little bit, that there are multiple quasi-stable states within the Fermi level of the material, and that quasi-level states enables the broadband radiation. So the setup of the experiment or the instrument is shown here in a different configuration. So as you can see, the main box A that holds all the circuitry, the T-ray source, detection system, and everything. And the XYZ, this scanner, three-dimensional, three-axis scanner, on which the wafer is mounted. The wafer can be, on this arrangement, to 8-inch wafer or 200 millimeter wafer can be accommodated from whatever small size is required. And then there is an aperture here marked E, which is not very clearly visible, it's behind the sample. The aperture allows one to control the power. Some cases we need higher power, some cases we need lower power, and that can be done with this aperture. So as a comparison of cameraless imaging technology, how it compares with the regular camera, where you have an object that is focused through a lens onto a CCD, or in general a focal plane array. and that CCD chip is giving out the signal that goes into the application-specific IC into the camera or imaging system that generates the image. In the nanoscanner, we don't have that focusing lens and CCD because we want to eliminate the limitations of the CCD. So the nanoscanner then scans a volume or an area, depending on what the user want to do. And that is recorded, and the data matrix is then what we call is a Beer-Lambert reflection matrix, could be transmission as well, but that is processed by specific algorithms built in our software, and image is generated. So the advantage is that we can scan a small area, big area, but also we can have low resolution and high resolution. We have a tremendous wide zooming capability from, as you say, sub-lattice to millimeter or whatever is needed for a given specimen or experiment. However, we have to be cognizant of the pros and cons of, the camera is shoot and record immediately. The terahertz or T-ray cameraless technique has some limitation, which is it's not a real-time imaging. We first scan it, and then the scanned intensities are converted into image. Image can be done in many different ways because of that. And lattice resolution scanning takes pretty long time. A lot of times overnight scanning is needed for even a 20 micron by 20 micron by 20 micron volume if we want to see really closely. But if we don't need to see that closely, let's say we want nano-scale, nanometer resolution, that may take a few hours. So, and another limitation is elemental analysis, like X-ray scattering probe that SCM can be fitted with. We are focusing on molecular events as opposed to elemental. So there's no elemental capability as of yet, and also it's not a handheld device yet. It's a laboratory or a clean room setup, but it's a setup instrument. Now, going back to silicon carbide crystal growth, this cartoon shows how exactly the process happens. I say some of the pictures on the left, those two pictures have been taken from the reference below. As you can see, Kimoto published a paper in 2016. It's a review paper, but he showed the process of sublimation and deposition or physical vapor transport, something, how it happens. So first you have the silicon carbide source, which is basically silicon and carbon material separately. And then they are evaporated at high temperature. And then there is a seed silicon carbide crystal. And then the vapors are evaporated silicon and carbon deposits on the seed crystal, simultaneously forming the crystal structure and deposition. So this is the most common process deployed in the silicon carbide industry up until today. Because by this process, one can grow a longer bull than other technique. So as the middle, this cartoon here shows, this is also from Kimoto work, that those are the kind of difficulties that can happen when bull is growing, there's basal plane bending, etc. That can happen from the seed crystal as the bull grows. But what is not included here, or what is not indicated here, is that this process, as you can see, silicon is being evaporated, carbon is being evaporated within the silicon, within the graphite crucible. Of course, graphite can withstand very high temperature, but some, at very high temperature, it does have an effect. The crucible is not totally inert at that temperatures. And some impurities can be introduced even unknowingly without any reason from outside. So, and also when this is induction heating RF coil, which is the coil goes around the crucible, and because of that heating arrangement, the temperature may have local variations within the deposition zone that is not easy to control. So there are, the industry is cognizant of that, and instead of the RF heating, they are thinking of cartridge-based heating, but still that is an experimental situation. Nonetheless, this local heating effect also can cause some imperfection in the crystal structure. But ultimately, when the bull is grown, is sliced, and the wafers are separated. So it is hoped that instead of RF heating, if they implement the cartridge heating, the temperature fluctuation will be minimized. And nonetheless, still, as we will show, let's go to the next slide. As you can see, I have images of two wafers, silicon carbide wafers. The left to the greenish colored one is simply we put the wafer on an optical scanner, like the scanners in your office. You want to scan a document or something. The same kind of scanner. We just scanned at a higher resolution. I think is 2400 dpi or something. So that is from the optical scanning that we see. But the same wafer, when we image with T-ray, it shows all the kind of things, structures that optics didn't see. So I have two examples of two different wafers here. And if we compare other wafers, here I have the most modern optical imaging, A and B, of two wafers. And the same two wafers are T-ray image on the right side. So optics does not miss 100%. It does still see, as you see, this feature, the one in bluish here on the optical image, much more details are seen with the T-ray image. And this is still a low resolution image. So this part is this part, this part is this part. It is seeing, it's not totally missing, the optics is not totally missing. This is the most modern optics instrument, A and B, and these images are produced from the most modern, quote unquote, $1 million optical instrument. So they see something, but not as clearly as the T-rays see. So in other words, what I'm trying to say here, what we see by T-ray image is not just totally an artifact. It is indeed there, except the industry have been missing it from seeing in great details as the T-ray is seeing. And also, this another wafer was done X-ray, just to see that how the most modern X-ray machine that can accommodate 150 millimeter wafer produce this image. And they, of course, produce a lot of crystallography data, which we haven't done yet, but we are able to. I'll show you. But this wafer is probably the same as this one, is upper right corner. And the same wafer, when you see with X-ray, X-ray doesn't do a good job either. But X-ray has its own purpose, which it does very well. But seeing all the features within the wafer is not one of them. That's what I'm trying to say. And then how do we explain all these features? Where are they coming from? What do they mean? That T-ray is seeing, T-ray is discovering, that remains a million-dollar question. But as you can see here, I have shown 5 wafers in the same sequence obtained from same board. So the grayscale and colored image both are from T-ray, but since it's in the same sequence of the wafer, one after another was separated from the boule, as you can see, the features in all of them kind of same kind of feature, except slight variation. And slight variation is happening because of the way crystal deposition happened. So that is the one of the things that we are trying to understand. So sorry about my rearrangement. So as you can see, we have to focus on the boule growing technology for us, for the industry to understand where all these features or all this pattern we see, where are they coming from? Mm-hmm. The other thing, so at this point, we actually are very skeptic of our own technique. That are we doing something wrong? Are we doing anything, missing out anything, that we see this pattern that nothing else has seen, and industry is doing well despite discovering all of these things. And so exactly what it is, and is it real? So then we have done one wafer in reflection as well as in transmission. The whole wafer was imaged in transmission as well as in reflection. So as you can see, side by side is the same pattern, except, the phase difference. Where I have white here, you will see the opposite phase of dark. The same thing all over the wafer. When it is dark here, it is dark here, that would be bright there. It is bright here, that would be dark there, because of the nature of the reflection and transmission. So
Dr. Rahman, if I could interrupt just one moment, please. So what we're looking at here in the patterns is the pattern not just on the surface. These are patterns that are in subsurface through the entire depth of the wafer, the silicon carbide wafer.
It seems like that, yes.
Okay. I mean, we could, your technology could then, and maybe you're going to get to this, slice through the different layers to take a look at the depth, and maybe you'll be getting to that. I just wanted to point out that
here I have not here, nor I mean that would be a good way of doing it. And again, we need a driver for us,
right,
to be able to get into that.
A driver meaning an interested party that wants to evaluate their wafers.
Yeah, I mean, this is a huge problem to solve on your own.
Right. Well, and you're making the tool. You're not.
Yeah.
You're not responsible for solving the industry's issue. You are making the tool to give industry the ability to solve their problems.
Yeah, and we don't mind solving it. We would like to be a part of it for sure.
You bet.
if there's an opportunity.
Through
So
collaboration.
yeah, collaboration. Yeah.
Okay, great.
I mean, it's better to work with a collaborator, with some other expert. Adding two brain is better than one,
Yeah.
so forth.
Sure.
But here, yeah, if we, I mean, for example, these wafers are about 250 to 350 micron thick. So if there was a way, and some of them has epi on these are blank substrates that don't have the epi on it. But yeah, if you could polish it, image it, that way, one thing. But we don't have to do that. We can do the imaging at different depths, at different layer thicknesses, and
Right.
that would be an interesting observation, which I think we should do sooner rather than later.
With optical techniques, if you want to see subsurface, you would have to remove a layer, take another
take another image
layer,
and
move on to
yeah.
Sure. Okay.
Polish an image, but we don't, fortunately, we don't have to do that.
Yeah.
So I think I am coming very near to the end of today's presentation. One other comparison is with silicon wafer. As you know, silicon is the most established technology. It has been there for a long time. They might have different kind of problems at the beginning, but they have fixed and cured all of them. So if you take two wafers, one silicon and one silicon carbide, and image under identical conditions, then side by side, their image is shown here. Silicon doesn't have any of those things.
Right.
Why? I don't know. Maybe they have perfected their process. Also, other thing is silicon is processed at much lower temperature, around 600 degree Celsius or so, while the silicon carbide is 2500 degree or so. So there's a tremendous difference in temperature as well. Nonetheless, silicon itself, this is a single crystal in 200 millimeter, 100 crystal. I'm sorry, 001 silicon wafer. This is manufactured by a reputable company, and we have all their data. So we see that there is no such pattern like this.
Right.
And this pattern is there. I mean, it's not an artifact. It is there. We have seen in more than one ways that is there.
And these silicon carbide wafers, the poly type on these are
4C, mostly 4C.
4C, and
yeah,
some of these variations we're seeing perhaps could be polytype variations.
Again, I am not sure, but I don't suspect a polytype variation because industry has checked on that more than anything else. Since they see the same polytype, they think it is something else. They do not suspect the growth process. So polytype variation may be a little bit, but silicon carbide is the most frightening kind of semiconductor. It has some 250 different polytypes. So it's good that industry can produce only one or two different polytypes. 4C and 6C are the most common. 6H at 4H and 6H are the most common ones. There's another one, 4R or something, I forgot, or 2R. Anyway, it's in the paper. But yeah, I mean, the polytype variation could be, but we are working with some other leaders in the same space, and hopefully we'll be able to find a little bit more with their help. And we are also let's see if I can show you the other thing. Let me go through this 2 or 3 slides more. But there is some other information that I would like to share as well. If not today, maybe next one. But so as you can see, compared to a silicon under identical conditions of imaging, silicon carbide does have something in it different than silicon. And here is another to show that is a lot more close or high resolution image, which shows in the epi layer, they have the grain formation, which we have to do more work on it. So moving forward, you mentioned about the polytyping. So this is silicon carbide high resolution image. On the left, you see lattice image of 100 nanometer by 100 nanometer by 100 nanometer. So it's very high resolution image. And that lets us to see, examine, and quantify the lattice parameters. So if I take only one surface from the cube, then this is image B is the only one surface of the cube, which is 100 nanometer by 100 nanometer. So now being in scale, we can do a graphical analysis and then measure the lattice parameter, which is obviously can be done from here using the full width at half maximum technique, which is a very standard technique in the industry and science. So I don't have the numbers here, but I believe these numbers were calculated and they are checked against 4H, which matched. I don't have those numbers here. Hopefully next one we can incorporate that. Okay. So in conclusion of today's presentation, by the way, this is a presentation which I made at the Advanced Semiconductor Manufacturers Conference that was held earlier this year in Albany. So in conclusion, we can say that T-ray images reveal clear patterns in the silicon carbide wafers, but not seen before by any other technique. Compared to optical and X-ray, T-ray images exhibit internal, what's the word here? Internal intricate patterns in silicon carbide with higher clarity, but you didn't see that in silicon wafer. So that's a contrast. These patterns are likely to arise during crystal growth process. That's our hypothesis. And we'll have to prove that or disprove that down the road. The variation in the reflected intensity is indicative of the presence of multiple domain walls. It seems like it might be coming from the fluctuation of the temperature within the zone, which may be giving rise to domain walls. Mm-hmm. This has been predicted by other researchers in the previous, which is the literature study is given in the paper. So we'll share that paper down the road as well. And both the reflection mode and the transmission mode images support this hypothesis. T-ray micrograph also exhibits many micro and macro domains, as I shown in one of the epi samples. Thus, T-ray images have revealed some intricate patterns for the first time. The crystal growth process may be perfected for the remedy of these kind of patterns. Mm-hmm. With that, I thank you for your attention, and we can move into any Q&A and other discussion.
Sure. Well, I think that the takeaway today, Dr. Rahman, is that the TerraSpectra tool and utilization of T-ray for a silicon carbide wafer or boule analysis. I mean, you could actually, take the measure, do the T-ray analysis on a boule. I know that's a lot of mass to be working with, but even prior to wafering the silicon carbide, you could do, if you had a willing potential collaborator, take the time and do lattice level work, surface and subsurface is what's important at the boule level. So I think the takeaway is the tool has a lot of capability, and it requires partnering with industry experts that are working in the silicon carbide growth and device manufacturing to work together in helping to improve the silicon carbide device functionality.
So you're absolutely right. I mean, we can make a configuration of tracking in situ as they grow via some window opportunity. But if not that, I'm sure industry has a way of remedying these difficulties once they know where it is.
Right.
Up until now, the industry is kind of blind. They don't have the eye to see.
Mm-hmm.
So
Well, I
we
think
have to
the ability for the TerraSpectra tool or T-Ray to do in situ observation of the process, given the proper mechanical setup, obviously, that should be very interesting to the industry.
mechanical setup, like you said. So it is not impossible because it's a non-contact method. Standoff distance can be adjusted. Therefore, if they can create a high temperature window into their reactor, that's all it takes for us to be able to probe it. Also, the other alternative could be that if they take a project and let's say grow, 1 millimeter, 2 millimeter, 3 millimeter, and 10, 7 or 10 samples of these, that will clearly show them that where in the process things are going different to give rise to this. As you know, a bull, when the bull is grown, the top portion and the bottom portion of the bull are not useful, but they are transpiring throughout the bull anyway, right? Whatever is happening in the top,
Right.
and growth and growth and growth. So they usually take the middle portion of the bull to make the wafers.
Mm-hmm.
But what is happening at the beginning is going throughout the process.
Mm-hmm.
So if they can see few millimeters and then another millimeter, another millimeter, another millimeter, that will give them a very clear idea where exactly this imperfection is coming from. And we enable them to see that. And they should be fixing it sooner rather than later, because if silicon carbide has to take off, as you know, it's still not the mainstream. Even though they are making some high-powered devices, but those are the peripheral devices. They are not the main. There's no computation that differs in silicon carbide as of yet. But when you are talking about very high temperature, harsh environment situation, then if you could build a functional IC with silicon carbide, wouldn't that be something that would help a lot?
Right.
So to do that, they have to fix these difficulties first.
Right. And of course, that's the macro and micro domain analysis of silicon carbide with T-Ray. That's just one part of the capability of T-Ray. Of course, we're talking today about just the micro and macro domain utilizing T-Ray, but the TerraSpectra tools have a lot of capability in analyzing and performing metrology on integrated circuits as well.
Absolutely. Absolutely.
Well, Dr. Rahman, we sure enjoyed having you again today. We will continue talking about silicon carbide, gallium nitride, other compound semiconductors utilized in the power device manufacturing and as well as optoelectronics. Thank you very much, and we'll look forward to talking to you next time.
Thank you, John. Pleasure is all mine, and talk to you soon again.
Bye for now.